Hello, everyone. I'm going to talk about diffusion of cosmic rays in the multi-phase interstellar medium. First, I'd like to show a long list of important implications of cosmic ray diffusion, from space-wider forecast to diffusive short acceleration to cosmic ray origin, heating, ionization, and star formation in SM, galactic wings and feedback in the intra-cluster medium, and indirect search of dark matter, cleaning of galactic synchrotron foreground for 21 redshift 21 centimeter signal. The resonance time of cosmic rays in the Milky Way is much longer than the traveling time along a straight path. It means that their motion must be diffusive. As shown here, cosmic rays interact with turbulent magnetic fields. They scatter off magnetic fluctuations and thus change their trajectory, showing this random walk diffusion in space. This diffusion in space also leads to diffusion in pitch angle, in momentum, and in energy. So this is related to the stochastic acceleration of cosmic rays. For the diffusion in space that I will focus on here, important parameter for quantifying diffusion is diffusion coefficient. The value I show here is the empirical diffusion coefficient based on the cosmic ray observations near the Earth. Although this value has been widely used in the literature, but I will argue that this is not a realistic value for describing cosmic ray diffusion in a multi-phase SM. And this has been already shown by observations. Observations suggest that the diffusion constant is not a constant. In particular, cosmic rays are found to be trapped for long periods near their sources with slow diffusion compared to this empirical value measured near the Earth. So naturally, cosmic ray diffusion depends on the properties of turbulent magnetic fields that they interact with. And as I will show later, turbulence properties are not homogeneous in the multi-phase SM. So accordingly, we do not expect a homogeneous diffusion of cosmic rays in the SM. Two basic parameters for quantifying the fundamental properties of MHD turbulence are sonic Mach number and alpha Mach number. Depending on the compressibility and magnetization of the medium, these two values can vary significantly across the sky. Because of the new gradient techniques developed, we can map these two parameters in different interstellar phases. And you can see that their values vary in different interstellar phases and even within one molecular cloud. So as I showed, turbulence in the multi-phase SM is not homogeneous. Depending on the values of MS and MA, the energy fractions of the three fundamental MHD modes, alpha, slow, and faster modes, have different energy fractions. And this directly affects the properties of turbulent magnetic fields in terms of the magnetic energy spectra and anisotropy. Both of them are important for determining the diffusion coefficient of cosmic rays. Okay, so MHD turbulence has different components. It has both solenoidal turbulent component and compressive turbulent component. They show distinctive properties. And as I mentioned, these three modes have different energy fractions depending on the sonic Mach number and alpha Mach number that we measured in MHD turbulence simulations. So this is reflected in the measured energy spectra of turbulence. For example, for the solenoidal alpha modes, we see the energy spectra is more consistent with the Kolmogorov 5/3 slope. And this has been seen in both MHD simulations in non-relativistic plasma, as well as peak simulation in relativistic plasma. But if you look at the compressive component of faster modes, and we see steeper energy spectrum. This is also seen both MHD simulations and in peak simulations. Observationally, we also see different energy spectrum of turbulence in different interstellar phases. What is shown here is in the warm interstellar medium, these are in fact density spectrum of turbulence. We found the Kolmogorov turbulence spectrum based on different types of measurements across many orders of magnitude in length scales. But if we move to cold interstellar phases with larger compressibility where stars form, we see significant deviation from the Kolmogorov component, from the Kolmogorov scaling. So this shows that in the warm phase, the solenoidal turbulent motion is the dominant component. So that is reflected in the Kolmogorov energy spectrum and Kolmogorov density spectrum. And here it shows the importance of compressibility, the compressive component of turbulence in cold interstellar phases. So we see deviation from the Kolmogorov scaling in density spectrum. Okay, and the different spectrum of turbulence is important for determining the energy scaling of diffusion coefficient for diffusion parallel to magnetic field. And this empirical value for the diffusion of cosmic rays has an energy scaling as 1/3. In fact, this corresponds to the Kolmogorov isotropic turbulence. But this is not realistic, as interstellar turbulence is magnetized, so it is anisotropic, and anisotropy affects the energy scaling of diffusion coefficient. So for a more realistic description, we need to take into account different MHD turbulence modes that give correspondingly different energy scaling of parallel diffusion coefficient. As example here, we set up a small fraction of the compressive faster modes, and we found the parallel diffusion coefficient has its dependence on cosmic ray energy changing with energy. It shows the dominance of different MHD modes in different ranges of cosmic ray energies like this given setup. Another important feature of turbulent magnetic fields is anisotropy. This has been well tested by numerical simulations. Along the turbulent energy cascade from large scales to small scales, the effect of magnetic field becomes more important towards smaller scales. So as a result, the anisotropy becomes more and more obvious towards smaller scales with more elongated turbulent structure at smaller scales. As illustrated by our simulation, even we start from a large isotropic structure because of the anisotropic turbulent mixing, we see it becomes more and more elongated and isotropic along the local magnetic field towards smaller length scales. So this means that in reality, when we measure the turbulent fluctuation along different orientations, we expect to see different level of turbulent fluctuation. We quantify this by turbulent anisotropy, which is the turbulent fluctuation measured with respect to magnetic field perpendicular and parallel to magnetic field. As the anisotropy depends on alpha Mach number, so this anisotropy measurement also provides another new method for measuring the important parameter alpha Mach number for MHD turbulence in different interstellar phases. Okay, so in terms of cosmic ray scattering and diffusion, the anisotropy is very important in affecting the resonant scattering of cosmic ray particles. Effective resonant scattering requires the size of magnetic fluctuation should be comparable to the gel radius of the particle. But because of this anisotropy, you see, when the parallel size of the magnetic fluctuation is comparable to their radius, its perpendicular size is much smaller than the gel radius. It means that within one gel orbit, the particle has to interact with many uncorrelated elongated magnetic fluctuation, leads to very inefficient scattering and accordingly very large diffusion coefficient and poor confinement of cosmic ray particle. So this would give you a large value of the diffusion coefficients. Okay, to summarize this part, depending on the sonic Mach number and alpha Mach number, these fundamental modes of MHD turbulence have different energy fractions. And these energy fractions are reflected in the properties of MHD turbulence, both magnetic energy spectra and anisotropy. And they both can affect the diffusion coefficient of cosmic rays, both its value and its scaling with cosmic ray energy. What we have worked on is to establish a direct relation between MS and MA values to the diffusion coefficient of cosmic rays. So in the multiphase SM, by observationally mapping these two parameters, we can determine the corresponding diffusion coefficient in a self-consistent manner toward a more realistic modeling of cosmic ray diffusion in the multiphase SM. For example, we already found with our numerical simulations, the diffusion coefficient for perpendicular diffusion, perpendicular to magnetic fields, has strong dependence on alpha Mach number. And this is different from the weak dependence on alpha Mach number in the literature by using wave description of magnetic fields instead of turbulent magnetic fields. We also found more recently, these are the parallel mean-free paths, which is directly related to the parallel diffusion coefficient. It has dependence on both sonic Mach number and alpha Mach number. So with these relations numerically tested and combined with the observationally measured MS and MA, we can get a more realistic description for the diffusion coefficient in both perpendicular direction and parallel direction to magnetic field. Okay, so the last part of my talk, I will quickly go through some applications of the turbulence-dependent diffusion of cosmic rays in different astrophysical environments. In the heliosphere, we found the interaction of cosmic rays with the heliospheric magnetic fields is important for affecting their diffusion. And that is a very important last step of their long journey before reaching the Earth. This diffusion is important in affecting the anisotropy in their arrival direction observed at Earth. Another example for the interstellar meteor in starburst galaxies, where the physical condition is quite different from our interstellar medium. It's cold interstellar meteor with a low ionization fraction and large compressibility. We took into account this different turbulence property in the interstellar medium, and we found the diffusion behavior of cosmic rays is quite different from that in our Milky Way interstellar medium. And we found that this can well explain the gamma ray spectrum of several starburst galaxies, as shown here. Okay, and another example is this cosmic ray diffusion near cosmic ray sources that I showed in the beginning. These are cosmic ray near supernova remnants that also interact with molecular clouds. And I found that by using the turbulence-dependent diffusion coefficient of cosmic rays, it can lead to the cosmic ray proton spectra and the gamma ray spectra more consistent with the observational data in comparison with this empirical model of cosmic ray diffusion based on the observation of cosmic rays near the Earth. So this again showed that the diffusion of cosmic rays near their sources and near Earth are quite different. The diffusion is not homogeneous. Okay, so as the summary, I stress again, diffusion of cosmic rays is not homogeneous. This is a very natural because diffusion of cosmic rays depends on the properties of turbulent magnetic fields, and that are not homogeneous in the multi-phase SM. And depending on so these relations and the properties of MHD turbulence relation to sonic Mach number and alpha Mach number, by observationally mapping these two parameters using different techniques, and also based on the theoretically determined, also numerically tested relation between the cosmic ray diffusion coefficient and MS and MA values, we can have a direct relation between the two, and then we will be able to have a more realistic modeling of cosmic ray diffusion in the multi-phase SM.